Here we are again, ladies and gentlemen. This is Jim Hendershot, ready to present to you lecture number 6 in this series of lectures on how to design electric motors and generators, or electric machines. This particular lecture involves the losses in electric machines. As we know, the efficiency of the machine is based on the output power versus the input. What percentage of the input power is transferred or transposed or converted into mechanical power? And so that process is the efficiency, and what reduces the efficiency or increases efficiency has to do with the losses in the machine. And so how are the losses distributed in a motor? Well, you have the input power going to the stator in the case of all these three motors. Then you have in the stator, the stator produces copper losses from the current flow in the conductors. That's called ohmic losses, and that's of course current squared times the resistance. That's the copper losses. And then also in the stator you have losses in the iron itself, in the steel, in the laminations, in the cindered material, which is made up of magnetic material. And since these machines are bipolar, in other words, the flux is north and then it changes to south, that means there's flux reversals. That means it goes through zero, and that flux is a dφ/dt, and it's based on the frequency of it is based on the commutation frequency and the PWM frequency that you use to chop the voltage to control the current, so that you get both eddy current losses and hysteresis losses in the iron. Now in the rotors are a little different. That depends on what kind of which of the three machines it is. The induction motor rotor has copper losses, but very little negligible iron losses. The hysteresis synchronous motor has some eddy current losses, but not too bad. No copper losses at all. The permanent magnet machine, depending on its design, can have eddy current losses in the magnets and even in the core, and certainly in the retainment sleeve if it's used to hold the magnets onto the OD of the rotor. But since there's no windings, there's certainly no ohmic losses or copper losses. Then you've developed mechanical power from the results of the input power and the efficiency of the energy conversion. So in the air gap and at the shaft, you have developed, you've converted that to power. But you have some additional losses now. You have the frictional losses of the bearings, or in the case of commutated motors, you have the frictional loss of the brushes rubbing on the commutator. In the case of these generators, these induction generators that are used for wind turbines, you have 3 slip rings and multiple sets of brushes, copper graphite brushes, which act like little brakes, and those are like little friction brakes on the shaft. So you have losses from that. And then machines that run high speed or even reasonable speed machines with real small air gaps like induction motors will have some windage losses as well. There are some other losses that take place in the air gap, stray load losses and zigzag losses, and those can be significant in some designs, but other designs, PM machines don't seem to have too much of that, but induction machines do. We've sort of defined what the losses are already. Those losses having to do with the current flow, or I call ohmic losses, or I squared R losses, and the iron losses have 2 components, hysteresis and eddy current. We'll look at those in a minute. And those eddy current and hysteresis losses occur in the stator, of course, but also can take place in the magnets, the cores, and retention sleeves. And then we already mentioned the mechanical losses from windage and bearing friction, and here stray load losses are because of current related load reactance fluxes. The specific losses in the machine, we can kind of look at those for other types of machines, and the wound field synchronous machines, they have windings on the rotor, so they have I squared R losses or ohmic losses in the rotor. But since they're synchronous and the rotors, even though they're laminated for, but not all. Some big motors use solid cast iron pole pieces, but there's very little dφdt or time rate of change of flux in the rotor pieces in a synchronous machine because the rotor's rotating in synchronism with the stator. And the induction motor is almost synchronized. It's very close to synchronous with very little slip. So if it's a low slip induction motor, there's very little iron losses in the rotor. But a synchronous machine rotor losses are always low. The retention sleeves can have quite a bit of losses in them. RSMs can produce eddy current losses in the rotor yoke, but again, as we said, they have no copper losses. Here's a kind of a machine losses versus power flow diagram, which helps you to break down the percentage of what these losses can be here. This is a very generalized if you have 5% losses or 10% losses in your machine, here's a rough idea of what the stator copper losses can be, the stator iron losses, or rotor. This is for an AC induction motor, by the way. And then your windage and ventilation and friction losses. See, when you air cool a motor, you blow air through it. That causes additional friction as well. The most serious losses, of course, are ohmic losses and iron losses. Those are the two we want to talk about the most. And the two components of iron losses are, as we said, are eddy current and hysteresis. And the frequency of commutation and PWM frequency and the flux density, as we've said before, has the most to do with determining what these iron losses are. And the thinner the lamination and the higher quality material, the lower the losses, and we'll look at some of those in a minute. And of course, the condition of the laminations. When you stamp a lamination with a die, you're subjecting the sheared edges to a very high stress, which tends to work harden the steel there, and this will increase the hysteresis losses in the material when you work harden it. So it's not uncommon for high performance motors to anneal the punchings after they're stamped in a hydrogen forming gas, and the loss calculations for these materials are based upon samples of each steel grade called Epstein strips, and they're mounted in an Epstein frame according to a standard test procedure, and loss data is determined for that in terms of watts per kilogram or watts per pound. And that published data from the steel companies is what has been used for the last 100 years to calculate the core losses in electric motors as well as transformers. These Epstein frames using Epstein strips, the methods used to test for core losses, were originally developed for testing the core losses for transformers, and transformers tend to be more rectangular than round, so the data isn't so bad from the steel companies if you're designing a transformer, but for electric motors it could be way off. Two very prominent historical motor engineers of the past that worked for giants such as Westinghouse and Reliance and General Electric, Tricky and Vinot, their names. They used this steel data from the steel companies to calculate the core losses in their designs before they had computers. And then after they built motors and tested them, they discovered that the core loss data wasn't very accurate, that they measured core loss data that was way beyond what they calculated. And so they tried their best to find out why, and we'll talk about why later. But what they concluded is that there's a difference in core losses between lamination strips or Epstein samples that have been sheared and either annealed or not annealed. They test them in all conditions, whether they're annealed or whether they're not annealed, but the only stress they're subjected to is the shear stress down the sides of these samples. These samples are like 12, 13 inches long and an inch wide, and so the percentage of the sample that's been work hardened by shearing is very small. Needless to say, they've tested samples that have been annealed and not annealed, and they don't find a whole lot of difference in them. So Trickey and Vinot, they came up with some correction factors. You can call them fudge factors if you like, but I like to call them error correction factors. And one of them used 1.5 and the other one used 2.0. And no one ever asked them why they didn't agree on this, but presumably one of them, since he was involved with large machines and the other one was involved with small machines, it's assumed that the 1.5 power factor is related to the large machines and the 2.0 power or correction factors related to small machines. Maybe that's an explanation for it, but we have no proof of that. So at any rate, the way you calculate your core losses is to use some formulas, which we'll look at in a minute, and look up the data provided by the steel companies and calculate the mass of the teeth in your stator and the teeth in your rotor and the yoke in your stator and the yoke in your rotor, and whatever frequency and flux density you calculate those portions of the magnetic circuit are being subjected to during operation. You multiply the appropriate core loss in watts per pound at that frequency and flux density times that amount of mass, and add these all up, and that's your estimated core loss for the machine that you calculate your efficiency from. But we're going to see subsequently the errors that can result from doing that. But I guess we don't really need to repeat this. It's kind of trite to say it, but all losses cause heating in the machine, and any losses reduce the efficiency. So the higher the efficiency, the lower the losses. The best thing to do is try to minimize the losses, but once you have whatever losses you have, you've got to get rid of them. You've got to use forced air cooling or liquid cooling or direct liquid spray cooling or splashing, spraying out of nozzles or splashing from the rotor end rings or little blades on the end of the rotor. You can cast on there in the case of induction machines. And of course, another thing that helps with the hot spots is to encapsulate the stator, or at least the end turns, in a good thermal conductive material, the types that I spoke about in an earlier lecture, that has high thermal conductivity. Some of these new thermoplastics and epoxies that are filled with the nitride materials and oxide materials that improve the thermal conductivity. Anything you do to reduce the efficiency or get rid of the heat caused by these losses increases your rated torque density and, of course, power density as well. So you could take any existing machine and cool it and increase its torque density, as well as trying to design the cooling abilities into a new design. We're going to talk more about this later, but it's worth mentioning at this point that large machines have the sources of heat, the worst source of heat, the ohmic losses, deeply buried inside the core of the machine. So you could think of the distance from where that source of the heat is created to where it's removed from the machine as the thermal diffusion path distance. So large machines have very long thermal diffusion paths distances. So you can get very rapid heating up of the copper wires if it's a long path from where they're located through the stator core to some cooling mechanism like forced air or by a liquid cooling jacket around the outside of the stator. So it's not uncommon to assemble cores in rotors and stators with cooling passages through them, with vent spaces between sections of the core, and the conductors in the stator and the rotor pass through these cores and are exposed to whatever cooling media is pumped through those. In large power plant generators, hydrogen and nitrogen is used to cool stators with long diffusion paths through these spaces. We're going to look at some of those parts in a later, when we study the lecture on cores and laminations. We'll see some of those parts and some examples of those cooling vent passages through the cores. But all those things improve the torque density of the machine. How do we reduce the electric losses? Well, the best way to reduce those is to make the conductors as large as possible, or use real strong magnets, so that minimizes the number of turns you need. So if in a permanent magnet machine, if you use the strongest magnets available, then you have lots of flux, so you don't need as many turns for the same amount of current. So what you do is you are able to use a larger cross-sectional wire because there's fewer turns in the slot, and this reduces your current density and your ohmic losses. In the case of an induction rotor, you can use copper bars instead of aluminum. Now, induction motors that ran off the grid, that were powered off the grid, they like to have aluminum bars because starting torque was so important that they needed high resistance for starting, so they used aluminum. That's not the main reason they used aluminum bars. They used aluminum bars in the squirrel cage of those machines because it was cheap, because they could die cast the aluminum. In those days when all those designs started, they couldn't die cast copper. Well, these days they can die cast copper. So there's no real need to use aluminum rotor bars in motors that are driven by inverters. You might as well use copper rotor bars if you have enough volume to justify die casting them, because you make a big difference in the efficiency of the machine by using copper bars instead of aluminum. We'll look at some comparisons of that. We have some actual comparison charts in our rotor design lecture for induction machines, and you could see that not only does it improve the efficiency, but it also reduces the heat in the rotor, because the ohmic losses in the rotors are lower because the current density is lower, because the copper has a higher has a lower resistivity than aluminum does. So the other thing we can do to reduce the electric losses is to not only to fill the slots with more copper or use stronger magnets, but we can also wind the coils with shorter end turns. We mentioned that before too. Then the other thing we can do to reduce machine losses is to punch the cores out of lower core loss materials, use insulating coatings on the lamination to insulate the interlaminar paths for eddy currents. You insulate those paths and reduce eddy currents, and then how you fabricate. It turns out that the main reason that the core losses on a tested lamination sample is much lower than what you get when you build the motor is because of the fabrication losses of the core itself. So that's a whole topic that we're going to discuss in a little while. But so the point is, if you measure, some companies nowadays, these core loss issues are so serious that they're measuring the core losses of the entire stator. We offer a service to do that, as a matter of fact. So you could try different fabrication methods of stators and measure the whole core loss per pound. You have to weigh the stator to start with, so you put it in the same units as the core loss published data for the lamination grades themselves, but you can compare what you lose. I think we believe that's what accounts for the differences that the two famous engineers, Tricky and Vinot, found was due to the fabrication losses. Stamping, hardening of the steel along the sheared edges from stamping a lot of slots, and then shorting of laminations one to another, even if they're core plated. If you have a worn die with big burrs, when you nest all the lambs the same direction, why you could short the lambs all along the sheared edge through the burrs. If you grind the OD of the stator core, which some people do, that grinding mushes the steel over, and you short the whole core from one end of it to the other at the OD. Now at low torques, low currents, that's probably not a problem on the OD because the flux density out there is low. But during times of peak torque, when the current is high, then the flux density out there could be pretty high, so you can have additional heating out there right at the OD where the lambs are shorted together from the grinding process. Designing a machine for smaller air gaps means that you need lower ampere turns to magnetize the circuit. This is particularly true in induction motors, so small air gaps improves the efficiency and lowers the losses. And if you have the space, make the cross sections of the teeth and the yokes as large as possible to reduce the flux densities, at the same time having enough winding space or core lengths to keep the current densities in the copper low. I was advised years ago by a well-known traction motor engineer from General Motors, who advised me years ago at a conference, that if you're stuck with slot fill problems and current densities, and you have to give up some core loss to keep the copper losses in check, then the choice between where do you run the flux density higher, in the teeth or in the yoke. And his advice was, and it's good advice, and I pass it along to you, that if you have to make a choice between where the higher flux density is, keep the flux density in the yoke as low as possible and run the flux density in the teeth up a bit, because when you make the teeth thinner, you gain a lot of winding space. But the actual mass of the teeth, you know, the kilograms or the pounds of steel in the teeth is probably quite a bit less than the pounds or the mass of the steel in the yoke. This is particularly true of low pole numbers. You know, 2-pole and 4-pole motors, that's definitely true. 8, 10, 12 pole, they're probably about equal. But for 4-pole motors and 2-pole motors, the yoke is far more mass than the teeth. And remember, losses are in watts per pound or watts per kilogram. So by running the flux density up a bit high on the teeth, you improve your current density, but you don't affect your flux densities penalty on core losses that much. Now the SPM and IPM machines, these are synchronous machines, and the rotor losses in these machines, you still have some rotor losses, and they're eddy current losses, but they're not too bad. They can be quite high in the magnets or in the retention sleeves, but it's not so bad in the core. We're going to look at it later when we look at materials, but one way to reduce these eddy current losses in rotors is to laminate the core of the rotor. Instead of making it solid, you laminate it, and of course, if you have an IPM, those very same laminations are what used to retain the magnets without adding an additional retainment sleeve that you can't laminate. So that keeps your eddy currents down in the rotor. You can have eddy currents in the magnet. So what's done there is to basically laminate the magnets. They don't call them laminations. They call it segmenting the magnets. You make a pole up of several magnets that are glued together before you finish grind or finish wire EDM or whatever you do to them. That's quite common. We're going to see some slides on that later when we look at the lecture on materials. But now magnet retention sleeves that are made out of wrapped yarn and tension around the OD, they don't have losses in them, so that's a good choice. But the metallic retention sleeves do have eddy currents in them. The rotors with solid cores can have eddy currents in them underneath magnets. Of course, we know about air gap windage, friction caused by a fluid or air in the air gap, then bearing friction. We know about those things as well. They're design issues, but there's not really much to say about them other than you have to calculate them or measure them. You can measure bearing friction statically with a torque wrench or a torque watch. If it's a small motor, you use a Honeywell torque watch, or if it's larger, you can use a torque wrench to measure the breakaway torque of the just by the bearings. Here's some little more discussion about eddy currents. You see in this example here, you have a solid piece of steel here, and you have a big eddy current path, so the magnitude of the eddy currents is quite high. But if you take that piece of steel and slice it up into a bunch of segments, and you have a very small eddy current path on each one, so the total eddy currents are dropped. Here's another example, all these little paths compared to this big one with a lot of concentrics around it. So this is a case that you could do that for a magnet. It's the same as what you would do for a laminated core for a transformer. It's the same idea. Here's an example of, I thought this was in the section on materials, but it's in this section here. Here's a case of laminating a pole. See, here's a pole that is that long, so this is made up of 3 radial segments that have been glued together, a little insulating layer in between them. And this whole thing's a North Pole, and that's a South Pole. This is a simplified way of looking at this. And what you can do is you can use a finite element batch files to solve for the eddy currents. Eddy currents is a function of the number of segments per inch or per meter or something like that. You could set up a batch file and make a bunch of calculations like that, and then you make a plot to determine what's a practical number for any given motor. You know, you get to a point of diminishing returns. And so one of the magnet companies, Shinitsu, a big well-known Japanese magnet company, they offer a service to take your design and run it through their software to tell you if you need segmentation of your rotor magnet poles in your particular application, and if you do, they'll give you a plot like this telling you, give you an idea of how many slices per meter or per inch is practical. You can increase it and reduce it, but you don't reduce it much. You see the slope is changing significantly here. See, and what is the relationship between power loss and hysteresis loop? I guess you know what hysteresis is. For a permanent magnet, we like hysteresis. For laminated materials, we don't like hysteresis. This looks like something like a permanent magnet. If I have a permanent magnet and I start with a field string, ampere turns, big coil, the flux would rise and come up the air, and then I would turn the power supply off, and so the flux would decay, it would come back, and so the stored magnetic flux density in that magnet stays at this value here. That's residual magnetism, isn't it? We like that for a magnet. We want lots of residual magnetism for a magnet, but for a soft iron laminated part of the circuit, that we're continuously changing the polarity of it, and as the motor rotates, and we're completely adjusting. We want the flux to be adjusted in there from the coils that are in the stator. Then we want this to be zero. We'd like this to go through zero or closest to it as possible. So this is a hysteresis loop of a soft material, not a very good soft material. It's got too much residual magnetism. And here's the hysteresis loop of a hard magnetic material, which is like a permanent magnet. By the way, these are backwards. This term is supposed to be over there, and this is supposed to be over here. Hard magnetic materials are permanent magnets, and soft magnetic materials are electrical laminated steels. That's a typo there. Sorry about that. Here's different ways that core losses have been calculated with a accuracy estimate. Steinmetz equations, modified Steinmetz equations, improved, further modified Steinmetz equations, loss separation model after Bertotti and dynamic hysteresis model, loss surface model. You can read about this in this publication here, overview and comparison of iron loss modules for electric machines. It's from, I believe it's from Italy, and how useful this is, it's not very useful to me, but if you want to make a big study of this, my suggestion to you is to make measurements, make your own measurements, and based upon how, make measurements on the cores and use that data to predict your new design, and then model it with finite element software and calculate the core losses, and using core loss data that you got from samples you've measured, and or use the steel data that you get from the steel company, but you're only going to have crude estimates of what the losses are going to be. If you use that method, you're going to have to use some kind of a fudge factor, and as you get a history of building motors and testing them, you can improve your own calibration factors. So what are the factors that affect core losses? Well, the thickness of the steel and the grade of the steel. And standard steel grades come in 0.35 millimeter, half a millimeter, and 0.65 millimeters. These are 3 gauge. The American grades for this are 29 gauge, that's the 0.35, and 26 gauge, that's the 0.5 millimeter, and the 24 gauge, that's the 0.65 millimeter. And the thicker materials have very high iron losses per kilogram or per pound. And these losses are based on published data, which we're going to look at in a minute. It's based on published data by the steel companies. But when you punch them, you put shearing stresses along the edges of where the punch sheared the slots and the teeth out. Now, a switch reluctance motor or a low-cost brushless motor that has 6 stator slots has a very small percentage of the lamination that has been work hardened by stamping, by punching, as compared to a large machine that has many hundreds of slots. It has 70, 80, 90, 120, 130, 150 slots. Then the very high percentage of the surface area of the lamination has been work hardened, and errors in core loss are going to be more pronounced in big machines like that. Work hardening of the sheared edges from the stamping process. So what's common to overcome some of these core losses of laminations is to coat them with a core plate or put an iron oxide on them. A very famous one is called a C5 core plate. And let's see, you can if you have a reasonable lamination that doesn't have too many slots in it, you know, let's say it's got 12 or 18 or 24 slots in a lam that's 4 or 5 inches in diameter, let's say. Okay, you could make a choice here. You could buy this 0.35 millimeter thick lam with an iron oxide coating on it, and you'd probably have the same core losses in your finished core as you would if you used a 0.5 millimeter lam, which costs less than this one, but if you had C5 core plate on it. So you would have better insulation interlaminar, and you can use a thicker, higher core loss, lower grade material if you got core plate on it. So Temple Steel in Chicago, they have a paper on this, and they make this argument that you can use lower grade steels that don't cost as much and wind up with the same core losses in the finished core if you use the C5 good insulation core plate between them. The other thing is, a lot of people make prototypes of small quantity motors. They bond the laminations together. There's 2 or 3 standard bonding processes using 3M has a special epoxy, a one-part epoxy that dissolves in acetone. And so you can dissolve, it's just like powder, it's like face powder. So it dissolves in acetone, you put it in a spray gun and you spray it onto both sides of the lams, and then you stack the lams up and clamp them together, stick them in an oven, and it bonds together. Makes a very nice core. And you see that layer of that epoxy, that very thin layer, maybe only 1,000 thick, that holds the lams together and holds the core together, that acts as your against interlaminar shorting for eddy currents. That's very effective. Now, some people have built their prototypes that way, and then they go to production and they have maybe their laminations automatically welded on the OD. And now their core losses are much different than what they were when they made the bonded prototype. So that's something to keep in mind and don't lose sight of. The other thing that we discovered in measuring core losses on finished samples, or finished cores, not finished samples, but finished cores, is if you go right on the production line and you take 10 cores off the line before the windings are put in, and you set them up and perform this core loss test that we have done, you'll find that the core losses vary by as much as 50% from one core to the next on the same assembly line. This is really mind-boggling and really complicates this whole problem of being able to predict what your core losses are. And we haven't proven what the true reason is yet, but we have a suspicion that we assume that the lams are all punched off of a die, and they're basically on those motors in succession. The die couldn't have worn much, so that the burrs didn't change much. So we conclude that whatever method is used to hold that stack together isn't repeatable from one to the other. And the most likely culprit is the clamping pressure. We found this to be true of welded stacks, so that if you clamp one stack real tightly together with a ton of force, when you weld strips on the OD over the center teeth, and then the next one you have a lot less clamping pressure. Like, for example, how would this clamping pressure vary? Well, it would vary if you had a fixture that you put a big washer on it and a big nut that you tightened up, or several screws or threaded fasteners that you had to torque down and tighten to apply the clamping pressure. So it's important that the tooling design, the fixturing, makes that clamping pressure repeatable. These are little tricks that are very important to try to keep your core losses repeatable. Welding, of course, cores can cause shorting as well. So the welding has to be done properly. Some companies will leave a big groove. They'll stamp a big groove in the OD of their stator cores to allow for welding. Then they put a big weld bead across there, and that is not the right way to weld. People think that, a lot of manufacturing engineers believe that when you weld something, you build up material. But if you use stamped laminations and you stack them up and you weld them by heating the material in a fine bead or a fine line using a laser welder or a TIG welder, a tungsten tip with inert gas environment, and you don't add any filler metal, there's no way you could build up and have the OD be larger than the lamination from that weld, because the stamped edges have a breakaway side. They're actually, one side of the lamb is smaller in diameter than the other side of the lamb. So when you melt and alloy the metal together, the result is actually a little depression of the weld, not a protrusion of the weld, but a TIG weld or a laser weld gives you an actual depression. And it's easy to test and prove that. So that, and the only place you might get a protrusion is where you start the weld. You might get a little tit there where you start the weld or end the weld. So the weld should never be started or ended on the core itself. It should be started or ended on a copper piece right next to the core. So you make the arc on the copper and then feed the torch, the laser or the TIG torch, across at a uniform rate across the stack of lambs, and let the arc be broken on a piece of copper at the other end of the core. Then you don't get any buildup at all, and you keep the welds as small as possible. It's better to have several small welds on the OD, and they should be like of the order of 1.5 millimeters wide and 1/4 millimeter deep. That should be the penetration to hold your cores together. And if you have 4 or 6 or 8 welds, depending how big it is, in the center of a tooth, and they're TIG or laser welded, you shouldn't have any core loss problems. But there again, you could test one that's been bonded versus one that's been welded. Try to avoid grinding the OD. It's better to turn the OD than it is to grind it. Another phenomenon that occurs with machines that have cores that are made and they're shrink fitted inside of big cast iron frames, fin frames. People who've done that have discovered that the radial stress on the yoke of the core of a stator will increase the core losses due to that constant stress on it from the shrink fitting of the stator core into the frame. And as a matter of fact, step motors, small precision angle step motors, they're so critical on torque angle accuracy, they actually don't shrink fit the lambs. They what they do is they bond them in with Loctite. They bond them in. They have very close fitting OD of the lambs, ID of the housing, and they bond them in with Loctite or with thermal silicon. Bond them in with thermal silicon that not only bonds them, but it dampens them a bit for noise, and thirdly, it provides a little better thermal conductivity between the laminations and the aluminum housing. Here's the core loss formulas. You could calculate the core losses for each of the sections of the machine, but you have to generate these Steinmetz coefficients for eddy currents and hysteresis losses. It's better to let a computer do that for you. Now here's a summary of core losses for different grades of American Institute of Steel. The electrical steel grades, the old grading system used these M numbers, M15, 19, 22. The smaller the number, the lower the core losses. And here's your watts per pound at 60 hertz and 50 hertz, watts per pound, watts per kilogram. And this is 1.5 Tesla flux density, or 15,000 Gauss. That's 15,000 Gauss at 60 hertz, and this is 15,000 Gauss at 50 hertz. And here's your core losses per pound in watts per pound. You're talking to 1.6 pounds, but and if you go from this is equivalent to about a half a millimeter, and this one's a quarter of a millimeter. So you see, let's do a comparison here. So your a very common electrical steel is this M19. So that with 26 gauge M19, the core losses per pound are 1.74 watts per pound. So that same thing in a thicker gauge, it jumps up to about 15%. So it's 2 watts per pound. That's a big difference. And as you can see, the same thing if you go up to real low cost, like these materials up in here. These materials here are the ones that are used in your refrigerator and ceiling fan motors and things like that. Twice the core losses of these steels here, you see. Then the M15 is the lowest of the silicons. Then you have to go to Carpenter 49 or to what's the other one? I forget what the other trade name of Carpenter 40, Hyperco 50 it's called. Hyperco 50. They'll have core losses of half of these again. Here's another list of core losses. Here we are at our 15 kilogauss, 50 watts, and or 50 hertz and 60 hertz. And it's all 3 gauges are listed here for most of the gauges for each of these. Here's the new IEC part numbers for these steels are listed here. See, the IEC, that's a European standard, they don't have exact equivalent grades to the American standard grades, but so their half a millimeter lamb is 0.0197 inches. Our half millimeter lamb is close, but it's a little off, you see. And so there's a slight difference in core loss, even though this is thicker, so the core loss is a little higher. But these are the charts that are used to measure core losses. The trouble is, these are given that for one flux density and one frequency, or 2 frequencies. And to calculate Steinmetz coefficients, you need more data than that. You have to have loss data for at least 3 different flux densities and frequencies. And that sort of data is becoming available. We talked about this topic here. We're going to come back to the availability of that new core loss data in a minute, but right now this is what I was talking about before, is that the standard, those core losses are taken under ideal conditions of sheared samples of each one of those examples of steel, and to advertise your steel as one of those grades, you're supposed to meet those standards. But each manufacturer is slightly different. But motor magnetic circuits they're not rectangular, they're not square, they're round, so that has an effect in this data as well. And as I said before, the core manufacturing process changes the actual losses from what you're going to use from that published data. Sometimes core plating is used on only one side of the lamb stock, so that's still, but you got to stack all your lambs to make a core all the same direction. You can't make that mistake. And here's some guidelines, again, based upon historical motor designs for air gap. Here's our air gap flux density, 0.6 to 1 Tesla for all machines, and the stator yoke flux density is 1.2 to 1.5. Stator teeth 1.2 to 1.7. You can run them higher. Rotor yoke 1.0, 1.5. Now, in classes I've given, I've presented this chart. Then I asked people in the class what kind of numbers they use in their company for the motors that they design, and boy, they give me all kinds of numbers all over the place. I'm surprised at the number of people that will run their flux densities up to 1.7, 1.9, 1.8 in the teeth and the yoke. I'm really surprised at that. When we study materials and look at the BH curves of materials, I'll show you the price you pay in ampere turns for to do that. You're better off to keep all the flux densities around 1.2 or below in yolks and teeth, because it doesn't take a lot of power to get it magnetized to that level. And as I said before, the flux density in the stator yoke, high flux density in stator yoke, affects the iron losses more because there's more mass there. Remember, another thing that you could do is you could use tapered stator teeth to help gain some slot area for winding and control where you put the higher tooth flux density. It's kind of a trade-off there that some people do. As we'll see, Toyota has done that with some of the Prius motors they've designed in the past. They've used tapered teeth for that reason. We're coming to the end of this lecture now, and this is a photograph of one of these Epstein frames I wanted to show you. So what this is a standard sample length, and an Epstein frame consists of 4 layer wound coils, and these are transformer type coils. There's a primary laid on there and connected to a power source, and then that primary has a sheet of insulation over it. It's taped, and then the secondary is wound on top of the primary, and they have a different number of turns and different wire gauges, but they're uniformly wound across there. That's important, and all 4 of these are identical. Then you cut these samples, and these coils have a very narrow slit in them, and so you take see that lamination strip, you take one of those lamination strips and you put it through the coil, and I see this frame even has a pin there to get them all lined up. So you make these samples with these holes punched in them, and so you lay one down, then one across it, then one across that, and one across that, and you keep doing that, and I don't know how many they put. I think there's 5 samples of each one in each one of these to make this rectangular core. Then you put a little weight on this to get them all to touch, and so you've got an iron circuit there, and what you do is you apply a certain current and frequency. And by the way, you weigh these samples so you know what they weigh. So you weigh the samples, build this frame out of them, weight down the corners so they're in contact, and then you apply a variable voltage and variable current and frequency to the primary, and by measuring the voltage generated on the secondary, you determine the losses in watts per pound or watts per kilogram of the material, and that's how they make the measurements that they use, that they publish. So they can adjust the flux density by the current, because they know how many turns there are. So you can adjust the flux density in each one of these by the fixed number of turns times the current, and because they know what the cross section are. They measure the cross section, and so they know how many ampere turns it takes to get different flux densities. So that's an input, and then you measure the transformed output voltage, and you know what it should be because of the transformation ratio between the primary and the secondary, but you don't get the same output voltage. You get something less, and from that they calculate the core loss. So that's the end of this lecture. Thank you very much.